So folks, in this section we're gonna be learning about math induction. I hope that you read the book before beginning this video. If you haven't, pause and please read the section in the book so you could have a better idea of what's going on. It turns out that there are two types of induction, one that we call weak induction and then we call strong induction. In this section we're going to be focusing a little bit on weak induction. And every induction proof is going to have two parts basically, a basic step or a base step, that's what we call it, an inductive hypothesis. In the inductive hypothesis, we pretty much assume that the theorem that we're trying to prove is true, and we try to show that the next case is going to hold. So I'll demonstrate all these things by doing a problem, example one, which says use math induction to prove that for all integers, the left-hand side of this equation is equal to the right-hand side of this equation. So I'm going to begin as usual with the word proof, and I'm going to be writing proof by induction. And as usual, I'm gonna let n be an integer. And the condition here is that n has to be greater than or equal to 1. And the very first step I see is going to be the base case, or the basic case, or whatever you want to call it, okay? And so in the base case, what you're gonna do is first look at your domain. In this case, the n is an integer that's greater than or equal to 1. So you're going to test the theory. You're gonna test basically the problem that you're gonna do. You're going to test if it works for n equal to 1. So in other terms, you're going to grab the left-hand side and take the first term from there, and that's going to be 4, and just box it. And you're going to do the same thing with the right-hand side and check out what the formula would give you. So the formula says 2n squared plus 2n, and is it true that the left-hand side will equal the right-hand side when you plug in 1? Keep in mind 1 is the domain, that's why we're plugging in 1, and so that's going to be 2 plus 2. Which is 4. So it works. The left hand side is equal to the right hand side, so at least the theorem is true for the base case. So now we can proceed forward to the next step, which is what we call inductive hypothesis. So in the inductive hypothesis, what we're going to do is basically suppose that the theorem that we're trying to prove is true and try to prove it for the next case. So in other terms, here's what we're going to write. We're going to say suppose that the statement 4 plus 8 plus 12 plus so on and so forth is equal to 2n squared plus 2n for some random integer n equal to k. K is basically some random integer. And what we would like to do in this problem is we would like to show that the theorem is going to hold for the next n, which is like basically k plus 1. So in other terms, we're trying to show that 4 plus 8 plus 12 plus so on and so forth plus 4n plus the next guy. The next guy would have been 4 and then n plus 1. We want to show that this is equal to 2 times n plus 1 squared plus 2 times n plus 1. Okay? So let's begin by showing the blue statement actually holds by saying let's grab the left hand side, and that is going to be pretty much all this. Copy paste, and yeah, let's see what we can do with this. So turns out that the first part of the sentence, or the 4 plus 8 plus 12 plus 4n all the way there, that is something that we already know information about. We have already proven that that is equal to 2n squared plus 2n. So as a matter of fact, we can take all these guys right here and replace them with pretty much 2n squared plus 2n. And we have the extra junk at the end, which is 4 times n plus 1. Okay, so again, because of the inductive hypothesis, this is true. So by inductive hypothesis. And now we're just going to need to manipulate the numbers until we get what we're looking for, which is basically all this. So like a little scratch work first of all. Let's kind of FOIL and see what our target is. So 2 times n plus 1, everything squared, plus 2 times n plus 1. If I FOIL this, I would end up with something like 2 and then n squared plus 4n plus 2 plus 2n plus 2 again, which is the same thing as saying 2n squared plus 6n plus 4. So that's my target. If I can prove that my problem up here gives me that, then I'm basically finished. So let's see. Let's go ahead and distribute the parentheses. 4 times n, and then 4 times 1 is going to be 4. And together, that's going to be 2n squared plus 6n plus 4, which basically matches with what we did on our scratch paper, basically. Okay, so since it matches, we can pretty much say that this is now equal to the 2 times n plus 1 squared plus 2 times the n plus 1, which is what we need to prove, which is what we wanted. So since the inductive hypothesis step was right and was correct, that means we are done with the proof. So therefore, we can say that for any n integer where n is greater than or equal to 1, we can say that the theorem actually holds. That means 4 plus 8 plus 12 plus so on and so forth, all the way up to for n is equal to 2n squared plus 2n by induction. And this is the end of the proof, QED. Okay.